So as we've already seen, TLB is essentially a hardware cache, right? So it has limited capacity. It could hold not many translation information. So whenever the capacity is, the maximum capacity is reached, the operating system or the hardware piece has to make the decision with respect to which TLB entry to evict and which one to preserve, right? Then we have to think about different cache replacement policies in this context. And two of the commonly used cache replacement policies that we're going to talk about and we will be discussing in the next few lecture is least recently used policies and random policy. Least recently used is also called LRU, which is one of the most commonly used cache replacement policies in literally any layer within the computer world, no matter whether we're talking about CPU cache, operating system page cache, block cache, like database memory cache, a browser cache, and so on and so forth. A lot of like different cache they are using LRU. So its intuition is a page entry that has not been recently used implies that it won't likely be used in the near future. Okay, so the least recently used is more likely to be the least useful entry that is highly likely to be evicted by the new entry. Okay, and the second commonly used policy is called random policy. In random policy, the core idea is pretty straightforward. You just evict an entry at random, and that's it. Okay. So about TLB workloads, this page translation workload, what kind of workloads the TLB benefits the most? The first type of workload is called sequential access. It's just like the array iterator, where we just scan through each and every entry within this array. And this is essentially some sequential memory access pattern, right? Sequential, as we've already observed, sequential array accesses can always hit in the TLB and hence are extremely fast because it eliminates most of the very first physical memory accesses targeting the page table entries. So this is the very first typical workload pattern that benefit from TLB, right? So the question is, what exact pattern would be extremely slow, would not benefit the most from TLB? So the highly random, without any clue to seek, this kind of extremely random memory access patterns with no trackable repetitive accesses, this would not be a good candidate for TLB caching. Okay, so let's first take a look at this different workload characteristic. On the left-hand side, we have workload A, which we've already seen in the previous example, right? So this is just sequential access to each and every element, sequential scan through the whole elements within an array, okay? So this is sequential. The second workload on the right-hand side, workload B. So let's first take a look at what it does. So again, it first declares a local variable, which is called sum, and then it initializes the random seed by calling this srand with a random seed number of 1, 2, 3, 4. And then it enters the for loop. And the total number of iterations with the first for loop is half a K, 512, right? So what it does is it random access within this array this many times, 512 times. The index is defined over here. It's a random, process, okay? And just sum all the values that you randomly draw into the sum. And then you jump out of the first for loop. You do another srand to assign another pseudo-random generator, to initialize another pseudo-random generator with the same seed That means the pseudo number sequence would be exactly the same as as we've already observed in the first for loop. You enter the second for loop, you perform another round of like random walk, right? So this is the second workload. So this slide shows the visualized access patterns between this and the difference between these two workloads. So as you can see, workload A is typically sequential. So it has two dimensions. The first dimension is a timeline, okay? And the second dimension is the arrest. So sequential workload, as time goes, you just perform monotonically, you just monotonically increase address, and then go ahead and access the next adjacent memory field, which is the next integer, 4-byte integers within the maybe the same physical frame. Okay, so this is sequential. And the second workload, workload B, it's random. So this is the very first for loop. Okay, for 512 times. And this is the second for loop, 512 times. Okay, as you can see, between these for loops, they show exactly the same pattern. This pattern gets repeated. This memory access gets repeated. Okay, at the same location. But within the same for loop, it's completely random and there's no clue. It's completely random. But between these two, repeated pattern. Okay, so the very first access pattern, we could call it spatial locality. And the second pattern, which is observed within workload B, we could call it temporal locality. So what's the essential difference between these two different kind of locality terminologies? Right? According to its definition, spatial locality, just like what we've seen in that sequential memory access, the future access will be within the nearby addresses, within the nearby like parameters in terms of the memory addresses. So this is called spatial locality. So let's say we have a memory block or a memory page. So a typical sequential access starting from the very first integer and scans through the rest of them, okay, linearly, all the way to the last. So that means if you bring in this translation information due to the very first access, all the rest would automatically benefit from the very first TLB miss. Okay, so this is spatial locality. So temporal locality means the future memory access will be just repeated to exactly the same data. Okay, so again, if you want to visualize it, so we have the same memory page again. So at time t1, it's this data gets accessed. At time t2, exactly the same data get accessed. So this is typical temporal locality. Future access will always be repeated to the same data that has been previously used, previously accessed. Okay. So the question is, what TLB characteristics held therein are best suited for each type of these two different locality properties, right? So it turns out, since, you know, TLB is special purpose hardware cache, which is used for what? Which is used for facilitating, accelerating the address translation process. So that automatically means there's this granularity mismatch. So what does a granularity mismatch mean? So for, let's say this is TLB. Let's assume it has just 4 entries. For each entry, it's mapped to a large memory page, let's say of 4 KB, right? So that means each and every small TLB entry gets mapped to a 4 KB page. So for whatever spatial locality, spatial access, within the range of this 4 KB memory page, it automatically benefit from caching this single TLB entry. So this specific TLB characteristic, this granularity mismatch kind of TLB characteristics are best suited, for the spatial locality property. It naturally benefit from spatial locality. And this is the very first characteristic. And the second characteristic is, since TLB is a cache, right? Since it has limited capacity, if the memory access workload is repetitive, meaning it preserves some sort of, temporary locality, the next access will just simply repeat one of the previous access. This automatic benefit from a TLB as well, because TLB is essentially a cache, hardware cache. It uses LRU, for example, to decide which one to get kicked out, to basically kick out those least useful, the least recently used entries. Okay, it's a small cache. So these are the workload locality and how the workload locality correlated with TLB characteristics. So next, let's take a look at the TLB replacement policies. So how exactly the least recently used policy perform within a TLB context. So let's talk about this interesting scenario, which is called TLB trouble. So in this slide on the left-hand side, it shows this virtual address of a process, and this virtual address space of this particular process spans like 5 different virtual pages, starting from virtual page number 0 all the way to virtual page number 4. And on the right-hand side of the slide, it shows the CPU's TLB hash. And if you look carefully at the TLB cache, it has exactly 4 entries. It has 1 less entry compared to the virtual memory capacity of this particular process. Okay, so these are the preconditions, the assumptions of this TLB trouble kind of situation. So let's assume at some point of time, there's a virtual memory access that is hitting on some random byte within the very first virtual page, which is virtual page 0. Okay, so since starting off, this TLB is empty. So there's a TLB miss, right? So this is a TLB miss. So flip the bit of valid bit from 0 to 1, and then you insert and populate this TLB entry. So the virtual page number field is 0, and the physical frame number field is just like a placeholder question mark. We don't care in this context. Whatever it is, we don't care. Okay, so this is a very first virtual memory access. And then this is TLB miss, obviously, as I've already said. And then followed by the second virtual memory access. Second virtual memory access. So it's stripe. So there's a stripe from that previous location to the next location. So right now, the second virtual memory access hit on some random bit, maybe within the same offset, but on the second virtual page, which is virtual page number 1. Okay, so there's another TLB miss, and you flip the valid bit from 0 to 1, and you populate the corresponding translation information with the virtual page number as 1, and no matter however physical frame number is, we don't care. Okay, it just question mark, leave as is. Okay, so there's another TLB miss. And then the third virtual memory access hits on the third virtual page. And you do exactly the same thing and populate. There's another TLB miss, okay? And you populate the third TLB entry, and then followed by the fourth virtual memory access. Another TLB miss, and populate the fourth TLB entry. And guess what? The next virtual memory access is going to hit on the very last virtual page, right? So as expected, the next virtual page, the next virtual address access take another straight away and target the last virtual page, which is virtual page number 4. So what would happen in this case to the TLB cache? Because right now the TLB cache is already full. Let's assume it uses LRU as a cache eviction policy. Okay, since it's full, it uses LRU. So what is the least recently used item within this across all the content currently buffered within TLB cache? Well, it should be this one, right? This is the least recently used entry. So it will go ahead and evict the very first entry. Okay, so now 0 is the least recently used item in TLB, and just go ahead, evict it, replace it with this newly updated information, which is a virtual page number 4. Okay, replace 0 with 4. And then interesting pattern over here is this thing will just simply loop back and go ahead, revisit, the very first virtual page, which is page 0. Okay. So what will happen to the TLB? Because we're using least recently used, and right now this is the most recently used. And which one is the least recently used? Well, this thing is the least recently used. Go ahead and evict this one, right? Go ahead and evict this one. Change it to 0. Okay. But as you can see, this second TLB entry is just the entry that will be accessed over here next, because from the high level perspective, you could already predict that, but somehow at the low level, this machine doesn't have enough intelligence to make the prediction, okay? Because it's just following an algorithm, which is LRU, okay? So there's another TLB miss. And you would just replace 1 with 0, which will be accessed in the near future, okay? So this is so-called TLB trouble. And because of this exact memory access pattern, and because this, slight subtle mismatch between the memory of the virtual address capacity of the running process and the capacity of the TLB cache, we have 5 versus 4, and all these, factors, they kick in, they play its own part, which introduces this so-called LRU dilemma, which is an awkward situation where you have to keep evicting out the item that you would reuse in the near future. Okay. So basically, the takeaway from the previous LRU trouble example is, it's not that least recently used or some other fancy cache replacement policies is always better, always smart. Sometimes a random is better than a seemingly smart, for example, LRU algorithm. Okay, so this is a major takeaway.